Okay, thank you to everybody to be here for this third lecture on, let me say, Kalman filters. Let me now, share better the material. Last time we concluded the lecture, you remember, with the calculations of the matrix L, which allows to place, very important word, the eigenvalues of an important matrix, which is the matrix of the dynamics of the estimation error. Okay, before going in depth of this, I would like to say, reconsider quickly this slide. We skipped. This means we will reconsider, but with the MATLAB. Let me reconsider just this slide here, the slide number 31. The reason is, in order to recall the concept of the matrix L. L recalls as Lundberg. No? Let me start from here. And then we will go ahead with the concept of the matrix L, place in eigenvalues, and so on. What is this equation which I wrote here in the middle of this slide? This differential equation, this dynamics, differential equations, let me say mean dynamics. This equation, or equations, but anyway, we have a differential equation and the initial condition. The differential equation is what? Says how it changes. Do you remember the concept of the derivative equals something? Let me express in this rough form. E error equals, this is written here at the beginning of the slide, let me say the state of state vectors, states or state vector minus the state vector of the system, which we will see basically, we will see in Kalman filter, I don't know exactly, also in Lundberger, or at least in this didactic introduction of Lundberger, I don't know exactly X, but I assume first of all, does X exist? In the sense, we model the system using this concept of the state. You remember energy and so on, and X hat represents its estimation, or its, in this case, we say properly observation. Observation means, as I told you last time, that I try to replicate, I try to observe X using the observer. Basically, to replicate, to reproduce, if you want to use some different words in order to have a feeling, in order to understand. Of course, X hat, let me say, is never equals X. First of all, because X, I don't know. But independently of this abstract concept, we will see that in this case, we have do you remember last time, an observer which is an asymptotical observer. I mean, assuming that I can know exactly the system. Do you remember this concept of the parameters? The example which I did in order to be more concrete is the DC motor. Assuming that I know inductance of the DC motor, assuming that I know the resistance, everything which physically characterize the DC motor, the observer which I presented until now is an asymptotical observer. This means I will reach the goal, let me say exactly the goal, and I will remain at the goal in infinite time. Of course, you can ask me, but why this abstract observer? which basically is a little bit moreover, I would like to say, could I use, it is possible, is it possible to use this observer? The answer is yes. I will go in depth today on this concept here. The first reason is if I introduce directly in a finite time observer is extremely complex. Moreover, as I told you, I anticipate now we can use also an asymptotical observer. Very often we use just asymptotical observer. The Kalman filter is asymptotical observer. Now we will go in depth also in this concept here because it seems to be, I don't know if last time, yeah, probably yes, I shared with the lateral camera what I intend before going ahead here. Let me clarify a little bit better or repeat a little bit better this concept of the asymptotical observer. And in particular in the concept of the Lundberg observer. Assuming that I know everything. You remember the idea in Lundberg observer, I know everything. But I don't know, excuse me, to be more precise, I know everything of the system, parameters, everything which characterize the system. But I don't know the initial condition. This is the our first, let me say, case. I mean, this is the real system, which the initial condition 1, this is the initial condition of the observer, which is not 1, assuming nevertheless that the parameter of the system is exactly the same. We will see a little bit better now with MATLAB. What I am doing now is exactly what I tried to represent it here. I mean, x hat, the solution of x hat, which I didn't put here, is different with the solution of x. If you want, I can write for you. The solution of x is x of t equal 1, which multiply as x, let me write, exponent function of minus t, because this coefficient is 1. I don't know if you remember math. If you don't remember, it does not matter. And this represents this profile. What is x hat? X hat is 0,5, the initial condition, with exactly as the solution of the, let me say, real system, but exponential, excuse me, with the same exponential. But the exponential profile is, as I told you, is exactly the same. But the profile of the solution of the which is here is not the same. But not only is not the same, we will reach, or better to say, x hat will reach x in infinite time. Now, is it useful, this one? Didactically is the first approach, but we can apply because we will see now with MATLAB, we can reduce arbitrarily this error over time. This means practically when the difference is, let me give you an example. If I want to estimate, for instance, velocity, when 10 up to minus 6 meter per second in the estimation of the velocity, 1 up to minus 9 meter per second is, of course, we can apply, but it's not this the real reason. Of course, this is the practical reason we can very well understand. The concept of the exponential function, which I implemented here, is the concept related to the model. I don't know if you remember in some lecture of mine. This model here, which could represent the velocity of the car, which is moving without input force. No, I am going. The car moves without gas pedal. Somewhere we'll stop, but in accordance with this model here, it seems that we'll never stop, we can see here. But of course, this is because we are considering an ideal, as an ideal uh, model without a static friction. I don't know if you remember some lecture of mine in bachelor and so on. This means also the observer in this case is conceived with this assumption. But in any case, assuming that I have a really in the system something like that, in order to reach infinite time, I have to conceive an observer which is more complicated than this one, assuming that this represents exactly the reality. Of course, if the reality is not exactly this and we will stop, I would like to say is somehow is intuitive that will stop also or I can consider an observer which we are achieve the goal in finite time, because if you remember the model of the observer reflects the model of the system. The system is an ideal system, but assuming that this reflects exactly something real, we can build a finite time observer, but extremely complicated. It's more complicated. If I had here the static friction, of course, the static friction is also here because, or at least I can consider here the static friction, and in this sense, of course, we can think. I will not show you. We can think that the observer can reach in finite time the real state. But of course, we have to work also in this case on the observer. Let me remain on this, and let me now go in depth a little bit here, which we can see if you remember in math. Thus, this equation here is an equation we reflect exactly the dynamics of the error, estimation error, and in accordance with the eigenvalues of the matrix A minus LC, I can speed up or slow down, but basically we try to speed up because in order to work with an observer or in order to observe what happens, the observer must be faster than the system. The system is characterized, or the dynamics of the system is characterized by the matrix A. And the idea is to obtain the eigenvalues of the matrix A minus LC much faster of the matrix A. What is the meaning of much faster? We will see now with MATLAB. Much faster means eigenvalues in absolute value larger than, the absolute value of the eigenvalues A minus LC much larger in absolute value, again, because the eigenvalue must be negative. I don't know if you remember, because otherwise the system, in this case the observer, is not stable. If it's not stable and the system characterized by eigenvalue of A is stable, or better to say asymptotically stable, we cannot observe because the dynamics of the error go to infinite. But very important, we will see a little bit better concretely with the example, must be larger, the eigenvalue of the observer in absolute value. Again, absolute value, I emphasize this concept here because of the stability or asymptotical stability. I will clarify a little bit better with this MATLAB symboling. Do you remember this theorem here, which I didn't demonstrate? To be more precise, the theorem I told you last time is going in both directions. It's correct, everything. I see if the pair A and C, do you remember the pair means the system which I am considering on the light of the observability, which is characterized by matrix A and C, is observable, then the eigenvalues of the matrix A minus LC can be placed arbitrarily, but the theorem goes also in the other direction. In fact, in the next slide, we can see if and only if. Why I put this theorem is just in one direction. It says everything is correct, but I put here because in some books they emphasize that given the observability, I can constructively design an observer, placing, very important word, the eigenvalue of the matrix A minus LC. Um, Roughly speaking, we can say that these eigenvalues is the eigenvalues of the observer, but basically it's the eigenvalues of the dynamics of the error of the observer, which I introduced until now. Let me see if I forgot to say something. Don't care about the proof because here we need introduce different other concept which I don't have time. This means I don't want to invest energy here. I will tell you just a little bit when I will open MATLAB. Why that? Because we can see here quite similar concept. What is the key point here? A transposed, C transposed, everything transposed. Also here, no, L equal K. What is K? No? Here is a little bit related to the proof of the system of the theorem. We can see here the concept of reachability is completely reachable. I don't have really time to go in depth on this, but I will tell you a little bit with MATLAB because we will look at one of these two command or the function in particular place. It's the same Acker or place Acker in honor of the Professor Ackerman. Yeah. Also. Also, this slide last time I skipped. I would like to skip also today because I don't have time to speak about the reachability because, of course, the reachability implies the controllability, but they are connected with the controllability. Here in this course, we are more oriented in observability and observer, of course. And this command here is just a tool, but I will tell you a little bit. Again, this theorem in Goe, let me say, is valid in both directions. We can see if and only if. This means the pair AC, the system, characterized in terms of observability by the matrix A and C, if this system is observable, then the eigenvalue of the matrix A minus LC can be placed arbitrarily. But if and only if means also that if the eigenvalue of A minus LC can be placed arbitrarily, then the system characterized by the pair AC in terms of observability is observable. Here is just in one direction because it's what we used. One certify the observability using the test. We are looking at this moment. We are still working with linear. Very important to remember. Time invariant systems. We will see that using Kalman filter, we will extend this concept. We will extend. And we will consider also time variant and in particular nonlinear systems. Just a few words about last time I skipped this. This red, let me say, red sentence at the end. A system is detectable if all unobservable state vanish into zero when time approaches infinite. I would like to spend a couple words about the sentence here because it's connected with the observability. As I told you, the course is oriented as monitoring, observability, observer, Kalman filter, and so on. The sentence I would like to say is intuitive, even though I didn't tell you about not specifically about unobservability. It's trivial to say if it's not observable, is unobservable. This means, if you remember, one possible definition of the observability that is not possible to observe, let me use now a concept which is here, but is not defined formally. This means which I cannot reach the state in finite time. This means unobservable. Now, detectable is if you think, and let me explain the sentence with considering with some considerations. It seems that the detectability, in accordance with this sentence here, is in a definition. I didn't put as in a definition just in order to relax a little bit the lecture, but is in a definition. Not only therefore because I didn't put any, as I told you now, any definition of the unobservability. At least not. I did introduce not in a formal way. But look, it seems to be that the detectability it's something which nevertheless allows to build an observer, assuming that the system is detectable but not observable. It is possible, because we have a part of the state which is unobservable, but that's gone to zero. This means I don't know if you remember my lecture in dynamical system, I repeat now. If it's going to zero, this means that this part of the system is asymptotically stable. But it's clear that if the system is detectable, I can build an observer because except for, let me say, in an initial part of the process, the system at the end or the observer will get the important, let me clarify it with words, the important states which I need, let me say, to control, or if I need, which I need to monitor. The reason is, if what I cannot observe is going to zero, after finite time, it could be negligible. Of course, this time could be, at least practically, could be also large. I mean, look at this. Assuming this state here, this state here is unobservable. Do you remember this was the real state, but it's going to zero. This means the influence of the state which works, let me say, works on the system, is nevertheless after, let me say, it is possible. Of course, it depends of the system. After a time t star could be negligible. Of course, this could be means could be it's very rough, no? Because if it's not negligible, okay. If it's not negligible, I can wait more time. But in any case, roughly speaking, it could be possible to use. It could be possible to use. Remain the word could because depend of the system. If I can accept thus until here, for instance, for this time, this system here, excuse me, this state here influences the state which I want to observe, but it's, of course, the observer cannot, let me say, roughly speaking, working well because the observer cannot estimate this part here, and as a consequence, they cannot estimate the variable which, let me say, I can use for control or for monitoring. This states, of course, is going to zero. This means somewhen, at least theoretically, are negligible because it's going to zero. The idea to tell you about this aspect here, which really is in a particular aspect of the observer, is another one. If I have an example in MATLAB, I try to show you a little bit better, but we can understand also with words. In this case, if in a part if in a part of the system is unobservable, if I have some state which I cannot observe, as a result, I cannot place all eigenvalues. This came uh, from the theorem, because it's if and only if. But of course, I can nevertheless build an observer, because even though I cannot, let me say, place all arbitrarily, very important, arbitrarily all eigenvalue, but it could happen. I can adjust with L11 and L21, as we see, as I defined last time, I come back now, stable eigenvalues. I can adjust, I cannot place arbitrarily. This means I cannot state the full dynamics of the observer. I cannot state this. But this part, which I cannot observe, is going to zero. Nevertheless, it could be that I can use the observer. Anyway, just to introduce this final part, if I have an example, I will tell you. Yeah, now we will go to MATLAB, but before going to MATLAB, let me repeat. You don't have to learn this, but this allows to open MATLAB, because in MATLAB I have exactly this example. Probably you remember in math for engineer, if you attended the class, if you are not engineer, no problems, you don't have to learn this. Just to understand the concept of the eigenvalues. Anyway, the determinant of lambda, to be more precise, is lambda I, but sometimes in some books, I is the identity matrix with the same dimension of the matrix A. But forget this concept here. Lambda in this form in some books also is an identity matrix in which the identity is in the diagonal matrix in which the diagonal we have the eigenvalues. Which eigenvalue? I tell you in one moment. At this moment, it's general eigenvalue. Therefore, sometimes we have lambda multiply I identity matrix. Nevertheless, with this condition here, determinant of this matrix here equals 0, I can calculate the eigenvalue. Here I cannot calculate the eigenvalue because I have to fix the eigenvalue, because the matrix A minus LC is the matrix parameterized, you can see here, by the element of the matrix L, L11, L21, we can see. This means here the problem is exactly the contrary. I will give two eigenvalues, and I will calculate L11, L21. I will be able to calculate if the system is observable. If the system is observable, strictly observable, it's not enough detectable. But nevertheless, if it's detectable, if I have an example I show you, we can do something. We can do something. We can adjust somehow. When is the critical point? When the unobservable state will not go to zero. If the unobservable part is not asymptotically stable, the observer doesn't work at all. Anyway, to work properly, the system must be observable, strictly observable. Again here, because probably for some students it's difficult, this concept here. The idea is to calculate L11, L21. We don't have to calculate by foot, by hand, because we have the function place. I will come back in 1 second with MATLAB. Here, in this case, I don't know if you remember, the case 1, 0, this means I will measure the first variable. Look, the matrix A is minus 1, 1, 0, minus 1. Let me come back. It's exactly the first system which I don't remember what it is. I lost. Yeah. It's this example here, but in the case of observability, let me say, we can see 1, 0, no? The system is observable. This is exactly the system characterized by the matrix, the transition matrix A minus 1, 1, 0, minus 1, the matrix A, and I am measuring each one. You remember I told you a lot about that. The case is an observable case. Then we will see what happens if it's not observable. If I do all these calculations, like last time I explained, no, you don't have to learn that. But for the engineers, it's easy to do this product, the sum between matrices. For not engineer, is not important, but look at the end, we have a matrix. We have this condition here. For the not engineer, that means determinant of this. Now, everybody can understand, nevertheless, the equation 1, because it's an equation which we have two variables, L1, 1, Ln2, 1, which, what is these two variables? Are the parameter which characterizes the matrix L, or the vector L, Lundberger vector. This came from the determinant. If you don't know what a determinant is, it's not that it does not matter, because with MATLAB, I mean, the goal of the course is not to repeat math, just a little bit. This equation, nevertheless, we can understand that somehow using this calculation, I will have equations in terms of L11, L21, very important, because we want to calculate this, and lambda. Now, do you remember I told you at the beginning, the idea is to fix two eigenvalues faster, now we will clarify with MATLAB, than the eigenvalue of the system. The eigenvalue of the system, the eigenvalues of the system are the eigenvalue of matrix A. But look at these two equations. Now we can understand really better, because I can fix lambda 1 and lambda 2, we will see with MATLAB. And we have here a system with two equations and two unknown, solvable because the system is observable, in terms of L11, L21. This means I will calculate this, but not by hand. Lambda L11, L21, once I fixed lambda 1 and lambda 2, then I have my observer. What happens if the system is not observable? Quickly, look, the system of the calculations are basically structurally the same, but look, the sensor is 0, 1. This means I am measuring x2. We can see here, I am measuring x2. Let me come back on the system in order to recall what we did last week, before last week. Look, with C equals 0, 1, the same system is not observable, because you remember, if I'm measuring here, I don't have information about x1, because I don't have this connection here. If you look at the calculation very quickly, the calculation is formally the same, but look, here, this is the case, 0, 1, 0, 1. Look, if you look at this final, or better to say, look at the equation 4. Here is just an exploitation of the equation 4. We have an equation in which just L21 appears. This means I have just a parameter, but the idea is to fix both eigenvalues. This is not possible from gymnasium. No? Also, the not engineer can understand this. No? If you remember in gymnasium, if I have two equations and two variables, it's easy to solve. Let me, roughly speaking, recalling you the concept of gymnasium. Two equations, two variables, yeah, we can do. It could be possible. Again, in our context, it's possible because it's observable. Here, we have the need to fix two eigenvalues, but we have just one parameter. The reason is, if you look at this calculation, let me say the parameter L11 will disappear because of the structure of the system in terms of observability, which in this case depends on the matrix C. Look, if you remember this, the structure of the determinant, how we can calculate the determinant, because of the presence of the 0, we reflect the not observability. For not engineer, a little bit difficult to I don't know if you did something similar in gymnasium. But anyway, the determinant means this element here, multiply this, plus, in this case, minus, this element here, multiply this, which is 0. This means 0 will annihilate L11. Therefore, we don't have L11. We can see here in this exploitation that we have the it seems that I can fix lambda 1 and lambda 2, but we have just one equation. I mean, we can see this system here reflects a contradiction. Let me say contradiction, because with L11, we have to fix lambda 1 and lambda 2. This is not possible. We can fix either lambda 1 or lambda 2, but not both. But do you remember the concept of the detectability? If the system is detectable, and this means that the system basically is asymptotically stable. Now, here the system is asymptotically stable. For engineer, it's clear to see that we have here two eigenvalues equals -1. But I don't want to go. I can show you with MATLAB if you want. For the engineer, it's clear that the matrix A two eigenvalues equal -1. This means then an observable part is asymptotically stable. This means I can build an observer fixing one eigenvalues and using L21, or better to say, I can fix an eigenvalue lambda 1, for instance. I can call lambda 1, but I can fix in a particular way that nevertheless the lambda 2 of the observer is nevertheless stable. Eigenvalue stable means its real part negative. I can do that if the system is detectable. I can place within particular choice of lambda 1 a lambda 2 at least stable with real part negative. Of course, I will have a particular L21. This means I cannot fix both arbitrarily, but I can build an observer. I can build an observer. If I have an exercise here, it could be that I have let me if I find some material to show you better this concept here. Okay, this part here we will see a little bit later, or I will come back when we will speak about nonlinear structures. Let me insist a little bit now before going in MATLAB Simulink. But I think we can go. We can go because I will recover this concept here in MATLAB Simulink, and it could be that we will see with MATLAB Simulink, and we come back here on this function here, which is the same like here. And yeah, it could be that I can come back here, even though I already clarified everything. We are speaking about continuous observer, no? Continuous observer. Here we have a remark. At this moment, forget this remark. It could be that I will come back next week when I will introduce the Kalman field. The Kalman field is a discrete observer. And at this moment, I told you just exist. No? You remember this exist, or this one exist, and Dunberg observer, which is discrete, which can see that is quite similar in the structure. I would like to say the same, but of course, conceptually, continuous and discrete systems are different. No? Okay, let me open MATLAB so we relax a little bit the lecture. I will repeat this difficult concept, in particular detectability and so on. But about the detectability, I'm not sure if I have an example in Simulink, but somewhere I did some calculations. But the calculations, if you want, I can do now. Also using this example. It could be nice. Let me see. before relaxing the lecture. Or let me see if I find already, because I did many times. Let me see if I find the calculation, or because I save time. 1 second. Let me see if I find. If I don't find quickly, let me see. Give me. I don't want to waste time now. It could be that it is better if I show you next time with already prepared calculations, because otherwise, in particular today, that I have to short a little bit. Let me give me please 1 minute more if I find quickly. Mm. I don't have here. Let me see. I don't have. Okay, let me go ahead, because today, as I told you, I have to conclude a little bit earlier. Let me show you MATLAB at this moment, but next week I have time to look at the material, and then we will do in a normal lecture. I will show you what I intend with this. Let me share again. What I intend with this calculation. I mean, if you do this product here, we have. Okay, let me sketch. Let me sketch. Otherwise, it's more easy. 1 second. Everything is. It's more easy to show you mathematically the calculations than to explain with words. 1 second with this. I have some problem with the connection. Okay, we have something like that. Lambda. Let me copy. Plus 1 plus L2. I sketch, and next week I will be a little bit more precise, but the concept I would like now, I spend energy to show you this. We have this result from the design of the vector L. No? If you do as in gymnasium, no? This multiplied this, I have lambda square plus lambda plus lambda plus 1 plus lambda multiply L21 equals 0. I hope no mistakes. Let me check. Yeah, I forgot L21. Right? Let me see. I forgot to. Yeah, I hope that is okay. Look, this means gymnasium. No? Let me do better. Lambda which multiply 2 plus L21 plus L21 plus 1. I hope no mistakes. If you remember in gymnasium, the ABC or the PQ form, I don't know if you remember. I know better the ABC, but it's the same. No? This means L12 equals 2 divided minus, if I remember the PQ form or the ABC form, something like that. Pico form. Meaning, and then we will see next week probably a little bit better. We can see that L12 depends on the choice of L21. This is the idea. But it seems to be possible to fix or to place two eigenvalues asymptotically stable. This means with real part negative. Of course, I cannot fix arbitrarily. Why not? Because we have just one parameter and two lambda. And two lambda. But if the system is detectable, it is possible. This is the idea. This is the idea. We will come back on this. We come back on this next time. Is this the case? No? The system is detectable because the system is asymptotically stable. The system is asymptotically stable. This means the part which is not observable, because the system, if I measure x2, is not observable, is going to 0. And I can place always, I can choose, let me say, L21 such that both lambda are real part negative. This means I can build the observer. Okay, we are speaking about asymptotical observer. Let me conclude the lecture of today with the MATLAB. Let me share MATLAB now. When I have a Zoom, for me, it's difficult to manage everything. Okay, now MATLAB is open. How can share now from here? Here is MATLAB, right? I have many windows which are open. Okay, let me go in the right folder. Here we are. Here. About MATLAB, I told you last time for the students who don't know MATLAB. I will repeat very quickly. Okay, let me start repeating MATLAB. Last time I told you that here in the middle we have the command window. To open MATLAB, you have to click twice on the icon. You can use also our research to work with MATLAB. Send me an email and I will forward to our technician and he will answer with information, with data which you need for connecting excuse me, for connection in remote. Please, very important. We have licenses, all possible licenses. We pay 30,000 euros per year to have all licenses. Please, at least for the exam, we need to produce the project in MATLAB. This means I mean, it is you have to use this toolbox here, and then send me an email. I will connect with the technician. It's extremely easy. You can work with all our resources from home. This is a big advantage. Okay, here we have the command window in which we can use, you remember, has a calculator, 1 plus 1 equal 2. A and S is the variable which contain, or the parameter which contain the value 2. Let me show you also this workspace, this part here. Let me clear everything again. 1 plus 1 equals 2. We can see in the workspace, in this part here, we have the variables of the parameters, which it's or there, and we have more than one value of the values. On the right part, we have the file which you have in the current folder. Please at home realize this also your folder. Here we have, in accordance with the Windows version of the MATLAB, we have here the path, where we are, exactly where we are. Let me open now this file here. The file here summarizes what I told you until now, and in particular, the observability, in particular the observability, is exactly the example which I described now, which is one of the first example, the abstract first example with variable x1 and x2, no particular physical meaning, but all possible physical meanings. For us now, it is important at this moment, this matrix here. We will see why I introduce also B, A0, we will see. And C. You remember, if I measure x1 is observable, if I measure x2 is not observable. Let me start with the easy example. The observable case. Look, forget at this moment this. What I'm doing here, I am testing if the system characterized by the paid, remember the notation A and C, is observable. We have a command in a function, let me say, it's in a command in MATLAB, OBSV, which consists of two arguments. This function consists of two arguments. Which arguments? A and C, no? The pair A and C. But of course, I can build this test also manually. Let me say manually. Rank is the command which allows to calculate how many columns or columns, let me say in this case, are independent. This is the rank. Do you remember I told you last time a little bit quickly about the rank? I don't have time to come back, but the students who attended the class of mathematics for engineer, you remember probably the concept of the rank. But anyway, let me for everybody recall this test, which is basically there now, no? Implemented. Full rank. Connections everywhere between the states. This is the practical meaning. Of course, rank is the mathematical concept which is related to the independence number of column, for instance, of a matrix. Column all row. No? I don't know if you remember my lecture. But anyway, practically means we have a MATLAB which help us, that we have connections everywhere. This means it doesn't matter what I measure, I observe all the rest. Not an observable part. C multiply A, and look. I can do the same, building by hands the matrix. Look, let me run the observability matrix. Forget this part here, because it's related to the another course. Let me look together with you the test. Look, OB to OBSB, once calculated using the MATLAB function, when calculated, let me say, by hand. Of course, rank, I use the MATLAB function. We have also a manually format to calculate the rank. This means it's totally observable. If I measure 0, the second variable, we will obtain some error for the second part, because we cannot directly build the observer. But we will see that OBS and OB, O capitalized, B capitalized, will be 1. Look, you have seen. This means it's not full rank, because full rank means 2, because the number of states equals 2. Do you remember? N is the number, today I forgot to say, but last time I insisted a lot, is the number of state. Practically means connections. We have both state connected. Here we don't have both state connected. This is a practical meaning. Of course, we can go in depth mathematically too. Let me conclude today because, as I told you, I don't have, would like to conclude 50 minutes before, as I announced at the beginning. Let me analyze this. Let me build the observer in the case of observability. Look, at this moment, forget this. We will see next week before starting the Kalman filter. P is the new the vector of the new eigenvalues. If you look at the lecture, you can see, let me come back. Or if you digit help place in the command window, but let me come back here. Where vector P, remember I told you that I tried to explain a little bit also this slide, where vector P transposed, about the transpose, a little bit too, in general, a little bit difficult to explain, because the function place is conceived for the controllability, but the controllability is the dual concept of the observability. Forget this just to justify, just to don't be scared if I am speaking about transposed. P is not a problem to understand because P must be in a vector, because C must be in a vector. But if you remember, C was in a row, excuse me, C must be in a column. But if you remember, C was in a row. This concept of the duality is connected also with the transposition of matrices. I don't have time to go in depth here. Therefore, we have also as a first argument, not A, but A transposed. But if you remember math, the eigenvalue of A equals the eigenvalue of A transposed. It's connected with this concept here. I don't have time to go in depth on this very important but very high, a little bit complex concept of system theory. But in any case, I tried to explain. Again, P transpose represents the vector of the desired eigenvalue of the observer. To be more precise, the column vector, but nevertheless the vector. Let me show you the design now of the observer using Simulink. This concept here with the eigenvalue in my complex, let me at this moment change. We will come back later or next week. With the place, the function place solves this problem which I defined before. Do you remember? I told you I need to calculate L11, L21, solving an algebraic system. Which one? This was 1,0. Using this calculation, I will obtain at the end equation 2 and 3, which represent an algebraic system in the variable L11, L21. Lambda 1 and lambda 2 are fixed. It's exactly 100, 200 in this case. But the MATLAB solves directly this problem, which should be done by hand. Lambda 1 and lambda 2 are exactly what I fix here now. Minus 100, minus 200, negative, because we need asymptotical stability. Otherwise, I will be unstable if it's not negative. Or stable, but also if it's stable, I I don't reach, even though in infinite time, the results. MATLAB solves directly because the system is observable. Let me open Simulink to show you how we can build an observer. If I click here on the file, you have these two files. I open directly an interface, which engineers probably know, Simulink, which is a graphical interface of MATLAB. Let me share. We can see here the system now characterized by matrices A, B, C, D, and not anymore by, do you remember this complex connections integral? But I can do that. We will be that is necessary if the system is not linear. Totally necessary is not, but is more suitable. Here I used to represent the linear system exactly what I told you during the first lecture, and I repeated last week at the beginning. Let me show you what I intend with this structure here. Here we have a matrix A, B, C, D, which about matrix A, B, C, D, I don't need now to repeat everything, why and so, but just to summarize, this is about matrix A, B, C, D, we have seen many things. This structure here is basically represented in Simulink. Alternatively, I can do something like that. I can do something like that. I will do during the semester for different structure because sometimes it is nevertheless I can use also ABCD even though the system is not totally linear. But if the system is not totally linear or for complex system, we have to build such kind of representation. We have to use that kind of representation as long as the system is, let me say, linear time invariant. Nevertheless, we can do really in a compact form using this structure here, in which here inside, I put it the matrix A, B, C, and D. You remember, I told you in this course, our D, our B will be always 0, but in practical example, in different projects, we can also have D not 0. We can do also with you some project. It's not difficult, but for the lecture, I prefer to show you this case because we have less information. In any case, we can understand better some concept because we have some particularity with D not 0, but it's not difficult. For project, we can take into account also D not 0. We can see here A, B, C, D, D, I told you, I don't remember, at the row of C and the column of B. And then I show you now B. Why C is an identity matrix? This is in a way to select an identity matrix because I would like to show both results, x1 and x2, in terms of observation. We can see two initial conditions for x1 and x2. It doesn't matter which one. What about A, B? C again, I clarified. No? C now I clarify. D I clarify, excuse me. Why 2, 0? Because zeros, because we have the structure of D. If you look at the definition which is here, is exactly what I wrote in my slide. If you look at D multiply U, no? In order to realize the multiplication between the matrix D and the vector U, D to be consequent with Y, the output, which is characterized by C, must be the same, must have the same row of C, the same column of B. Think about that. We can discuss also next time. Now I have to go faster because, as I told you, I have to conclude a little bit earlier. Let me go in MATLAB in order to show you the matrix A, B. Where is MATLAB now? Here. B is the matrix 0, 1, because the input in the second channel, let me say. Therefore, I put here B. Now, observer. I am concluding. In the observer, if you remember, I have the model. And until now, we are considering the model exactly, and the model which reflects exactly the system. This means no difference between matrix A, B, C, D in the observer, we will see the dimension of the matrix B, which we have here, is, or at least we have a particularity of the observer, but the model characterized by the matrix A and B is exactly the same. It's an assumption. I don't know if you remember the calculation of last week. I assume that I know perfectly the model, or at least I know perfectly the system, and I know the model reflects exactly the system. In the Kalman field, if this is not valid, we have some problems. I told you last time. And this problem could be, I don't want to say totally solved, but could be managed by the Kalman field. We have two inputs. You remember last time I told you the U as in the system and the error between what I am measuring and what I am observing. We are measuring x1. Here, C, what when this means from the vector which we have in output, x1 and x2, I am measuring x1. We can see, in fact, here, I will compare with the first element of this max, the max the max, excuse me, the max. Here we have the vector, we will see x1 and x2, like here, because C is also here an identity matrix. And then I will take x1. This block here, next week I show you where you can find also the block. Now I have to proceed a little bit faster. Allows to distinguish x1 and x2. Let me go here inside because I would like to show you an interesting part. Look, the matrix B, this matrix B here, is characterized by two elements. The matrix B with the model, exactly which I defined also for the real system, and the vector L. Which I calculated using the function place. D, in this case, as I told you, consists of a matrix 2 times 2, because as I told you, consists of the same number of row of C and the same number of column of B, this B, in this case. Because we have two inputs, one related to matrix B of the system, of the real system, which is the same in the model, one related to L, which is the error, what I am measuring, what I am observing. Initial condition is different. I don't know if you remember. I don't know if you remember in the lecture. No? The idea is to show how, despite different initial conditions, I will reach the value asymptotically, mathematically asymptotically, theoretically never, no? Or infinite time, better to say. Let me show you the simulation. We will go in depth next week. And in any case, I have to start with the Kalman next week. Let me cancel this noise here because I will use next week to introduce the Kalman filter. The Kalman filter we will see will be introduced considering errors in the model and the noise in the measurements. Keep in mind, at this moment, no error in the model, no noise in the measurements, which is not realistic. Look here. The observation, for instance, of x2. We can see that despite the initial condition, which are not the same, it seems to be the estimation not so bad. Of course, mathematically, I will achieve the state in infinite time. It seems to be that we achieve here, but it's not the case. But it's not the case. May I can achieve also temporarily the real state? Yes, if I put complex eigenvalues, then I will oscillate. I don't know if you remember. I will oscillate on the real state. But of course, the error will go to zero asymptotically. This does not change. I show you what I intend. Do you remember here? I put it before. I put it before two complexes conjugated, because if you remember the Gauss theorem, the eigenvalue, if the eigenvalue is complex, they are conjugated. No? Let me run. Before running, let me show you again the results, because otherwise we cannot understand what I intend. Here we can see, nevertheless, that the error remains, in this case, I would like to say always positive, because the blue line is always under the, let me say, the yellow line. It could be that once I will cross, it could be, let me see. Yeah, I will cross one, but just one. If I want to oscillate around yellow, I need complex eigenvalues. Let me run the data. And let me run here the simulations. Yeah, we can see also from here, no? That I am going up and down, up and down. Let me say in this form here. Could be an advantage. I would like to say it could be. It depends. It depends how we measure the error. No? Typically, if the oscillation is not so high, it is an advantage, because it depends of the norm. It's a little bit more complex to define. In this sense, the norm of the error, no? This in this sense here. In any case, we can understand that it could be an advantage, no? Because the error is not polarized positive or the negative, but yes, it's more complex to define is better or not. I will tell you about that when we will see a little bit in Kalman filter the norm of the error, the norm of the error, the measure of the error. But nevertheless, this very often is an advantage. If the oscillation, of course, does not disturb the functionality of the system, because we can understand that for some norms, some way to measure the error could be less the estimation error. But about the measurement of estimation error, I didn't tell you now. Therefore, it's difficult for you to follow me. The last thing which I want to show you, look here. Here we achieve, let me say, good result. Let me formulate this in this form here. Relatively quickly, 0.05. But we pay this result within a picking. It could be that this is 700, remember here, is not acceptable. What we can do, as I told you at the beginning, I can place arbitrarily the eigenvalues. This means this peak or the picking effect is due to the fact that probably it's too fast, the dynamics of the observer. This means at the beginning react very strongly. This means, look what I intend. If you put here, for instance, 20, we will oscillate because the eigenvalues is complex. About the solution complex, and so I will come back a little bit, but I don't next week, but I don't have time, believe me, to go in depth on the solution of the differential equation. This I did in dynamical systems, in math for engineers, and so on. Let me run now. But now, do you remember the concept of placing arbitrarily the eigenvalues? Faster and faster dynamics means larger and larger eigenvalue, the real part eigenvalue, the eigenvalues in absolute value. Now, the eigenvalues is less in absolute value. Instead of 220, I'm waiting for slow observation. This means the error, the dynamics of the error will be slow. I will converge slowly, but probably I will have a picking phenomena a little bit less. Let me show you. Significantly less, I would like to say, because I reduced 10 times. No? In fact, look, we can see the picking, it seems to be less. Not much. Yeah, in much. In 770, 10 times less. It seems to be linear, but it's not. But in exponential function, because the solutions are exponential, at the beginning it's almost linear. Do you remember math? Therefore, it seems to be 10 times less because I am 10 times less eigenvalues, but it's not exactly so, but can be approximated because at the beginning, we are at the beginning of the solution, which are exponential solution. The exponential function could be approximated, you remember math, with a linear function. But of course, the time in which I am crossing is also 10 times larger. Okay, the idea was to conclude a little bit earlier. I was not able, but I have to close now the lecture because I have to go to another meeting. They wait for me. Excuse me for this, but anyway, the lecture is more or less the same. The time, I respected the time. But the idea to close at least 15 minutes before, earlier. Yeah, we will see. If I have a question, I have time for one question. But we can reconsider the question next week. The lecture will be in hybrid form. This means I will be in Corazzuse, exactly as is written in my study where I am. I hope that you can come. If you not, if you not can come, no problem. If you cannot come, excuse me, no problems. The lecture go ahead also in this form, but the hybrid means parallel. No, I am in room, I am in the room, and you can nevertheless, if you cannot come, you can attend the classes per Zoom as today. If no question or one question at a time, I would like to stop to record.